This tutorial teaches Brent method, and if you go in your book to page 209, there's a problem related to pipe friction. And in this, if you remember from your fluid mechanics or water resources class, there's an equation called Colebrook equation that relates the friction factor of a pipe to the roughness of the pipe, which is epsilon in this case, and the Reynolds number of the flow through the pipe. And this is a non-linear equation and very difficult to solve. If you know the Reynolds number and you know the roughness of the pipe, what is the friction factor of the pipe? And if you remember from that class, friction factor itself changes depending upon the flow conditions, that is the Reynolds number. So it's a very complicated problem and very difficult to solve. And one way we do it, we use Moody chart, which is an implementation of this equation. We basically have E over D and Reynolds number, and for various E over D's, we create a relationship or a curve between F and Reynolds number, and that's the way we end up solving it. But in this tutorial, we will solve this method using Brent method. Now, you don't have to code up Brent method because Brent method is built into Matlab. So there's a program called F0, which in other words says find the root of a nonlinear function, and it basically includes all possible solutions because it will cover linear solutions as well. And if you go all the way to the bottom of this tutorial, oh, by the way, this is a good point to show you where to go for help if you need to find help on Matlab. This is www.mathworks.com/help/Matlab, and this is a reference in which I have put F0. If you just Google search F0, you will most likely land onto this page. And if you go to the end of this page, you can always find out what are the references for this particular code. And I would highly recommend, if you use a Matlab code to do some manipulation or computation in your research, make sure you cite the appropriate reference. In this case, this F0 is implementation of Brent's algorithms for minimization without derivatives. So make sure you cite the appropriate references when you use a Matlab code. So now we go back to the book, and you can see that if you go to the next page, it creates a function called g of f. And of course, if you look at the graphical method and if you plot this function, you can see that it crosses the 0 somewhere around 0.03. So let's go ahead and set up this function. So if we look at the implementation of this function, what we see is that we have a function that we are trying to find the 0 for, and we provide an initial value and pass it through F0 to get our solution, which is a very straightforward implementation. We can also have some options that we may talk about that we can set up, like how many iterations we want to set in case the program becomes a runaway program. Just like in the other implementations, we set it to 100, that if we can't find a solution until 100 iterations, then stop it. So let's go to Matlab, and I have already copied those 4 lines over here to look at the plot, but let's break it down. So these are the parameters of the problem. Here is the Reynolds number that we calculate. Here is the Colebrook function or equation, to be precise, and then here is the function plot. Now this is a new command for you because we have been using plot function before that plots 2 arrays. In this case, we are plotting a function, And if we look at the definition, how we define this function, we use an at symbol with parentheses with f. So we're saying g is a function of f, and this is the definition of that function. After that, we put a space, and then we put the mathematical equation, which is 1 over square root of f plus, the whole Colebrook equation. And so this is a function, and then here I'm saying plot this function g between 0.008 and 0.8, and make sure you place the grid so I can see, put the x label to be f and y label to be g of f, and that's it. Let's run this code, and let's save this as Colebrook. Okay. And you can see, we see exactly the same plot that you see in the book. So now we go back to the book, and we can see that we can implement this function, the Brent method, through F0, where we provide the function name and then the initial value. In this case, we are starting from 0.008, which is right here, and we hope that it will converge to our solution. So let's do that. We go back here and we say F0, find the solution for our function, and our initial value is 0.008. And oops, I think I put an extra 0 there. And it converges to 0.029, which is the solution. Now it's worthwhile to see what happens when what happened here. So it aborted the search, and that is because it reached a point where it found a complex solution. And of course, we are looking for a real solution, and that's why it aborted the search, because it couldn't find the answer, and by default it put the answer as not a number, which is often useful in computations. So whenever it encounters a complex value, it aborts, because it expects you to use a different function which probably will handle complex functions of complex variables. So this concludes this tutorial. Make sure that you go through this section 8.4 in your book and understand how this implementation is done and what it means.